Today I am going to explain you about the Francis turbine. Francis turbine was designed and developed by the scientist named James B. Francis. Francis turbine is inward reaction turbine. We have two types of turbine, that is impulse turbine and reaction turbine. In impulse turbine we have the Pelton turbine. In reaction turbine we have Francis turbine and the Carbonic turbine. Today I will explain you about the Francis turbine. Now Francis turbine we have the radial discharge at outlet, that is the old Francis turbine, and in modern Francis turbine we have the radial inlet and axial outlet, means the water will enter radially inside the runner and it will leave the runner axially, that is the Francis turbine. Now Francis turbine have a different component. First component you can say that is the scroll casing. So casing that will be used for distributing the water to the guide vanes. Second we have the penstock. Penstock, that is a large conduit that will be used to supply the water from the reservoir to the turbine inlet. Then we have the guide vanes. So guide vanes are the, we can also say that is the fixed vane. So water that is coming from the reservoir will enter into the casing, and from casing it will enter into the guide vanes. So the guide vanes will guide the water towards the runner. These guide vanes are fixed at one point. So the angle of guide vanes can be changed with the help of the governing system. So governing system that will be used to vary the flow of water according to the load on the turbine. That is the governing mechanism that will be used to change the flow of water according to the load on the turbine. Then we have the runner. Runner, that is a circular wheel on which we have the vanes. So these vanes are also called as the moving vanes. The water that is coming from the guide vanes will enter tangentially at a tip of the runner, and it will leave the runner at axially. So that is the runner. Then last we have the draft tube. Draft tube that is used for the discharge of the water from the runner to the tail race. So these are the components of the Francis turbine that we have seen. First is the penstock, second is the scroll casing, third is the guide vanes, fourth is the guide mechanism, fifth is the runner, and last is the draft tube. Now we'll see the velocity triangle for the Francis turbine. So here I have drawn the velocity triangle for this one is for the old Francis turbine and this one is for the modern Francis turbine. Okay, so here in case of the old Francis turbine, water is coming out through the runner radially. In case of the modern Francis turbine, water will enter radially and it will discharge axially. So you can see here that the water is entering here, that is the inlet side, and this is the outlet triangle. This one is the inlet triangle and this is the outlet triangle for the Francis turbine. So here the V1, that is the velocity of the water that is entering into the runner. Here we have the VR1, that is the relative velocity. Now VW1 and VF1, that are the components of velocity V1, and U1, that is the blade velocity, or you can say the tangential velocity also. Alpha 1, that is the guide blade angle, and beta 1, that is the inlet blade angle. Same way here the water will coming out radially. So here the value of alpha 2, that is a guide blade angle, that will be equal to 90 degree, and here the water is coming out relative to the blade. So there we have the velocity, that is a VR2. Here angle is alpha 2 is 90 degrees. So here VW2, that will be equal to 0, means the world velocity will be 0. This U2, that is the tangential velocity at the outlet. Here the value of VF2, or you can say the velocity at the outlet, is same as the flow velocity VF2. Okay, so this is the outlet triangle for the modern old Francis turbine and inlet triangle for the old Francis turbine. Here you can see the water is entering radially and it is discharging axially. Here the value of beta 1 is 90 degree. Now this here it is a 90 degree, and here the value of beta 1 is less than 90 degree. Okay, so this is depend upon the degree of reaction. A degree of reaction that is defined as the ratio of change in pressure energy in the runner to the change in total energy in the runner. Means in this case, if you derive the relation, and according to the relation, the value of the beta 1 will be equal to 1 by 2, that is the 50%. Okay, so here the value of beta 1, if we put in the relation of a degree of reaction, that is beta 1 equal to 90 degree, then it will be the degree of reaction will be a 1 by 2, so that is 50%. So according to that degree of reaction, we have the different type of runner, that is slow, medium and the fast runner. So in case of this modern Francis turbine, we have the medium type runner, and in case of the old Francis turbine, we have the slow type of runner. Okay, so here the value of beta 1 is 90 degrees. So in modern Francis turbine, we have the medium type of runner, and here you can see that is again we have guide bed angle, that is alpha 1, velocity of the water that is entering into the runner V1, velocity component of V1, that is VW1 and VF1. Here the beta 1 is 90 degrees, so the relative velocity will be equal to the VF1. Here it is you can see the outlet triangle. So outlet triangle, again we have the velocity VR2. Here also we have the axial discharge, so it is alpha 2 equal to 90 degree. VW2 will be 0, U2 that is the tangential velocity, and here the velocity leaving the blade, that is equal to the flow velocity VF2. So these are the velocity triangle for the modern old Francis turbine, and this is the velocity triangle for the modern Francis turbine. Okay, see the work done by the runner. So work done per second, I have written the equation, that is rho q VW1 U1. Now how this equation comes? We know the relation of work done for the jet, that is acting tangentially at one tip of the blade, that is rho q VW1 U1 plus or minus VW2 U2. Now here you can see the value of the VW2 is 0. So if you put the value of VW2 in the equation of rho q VW1 plus VW1 U1 plus or minus VW2 U2, so VW2 is 0. So the remaining term will be rho q VW1 into U1. So the work done per second will be rho q VW1 U1. In place of q, you can put, that is q is equal to AV. So our equation will be rho AV VW1 U1. Now second one is work done per unit weight per second. Work done per unit weight per second. So per unit weight we have to divide by mg. So here if we divide by mg and if we derive the relation, the final relation will be VW1 U1 upon g. So if you have to find the value of work done per unit weight per second, then you have to use the relation VW1 U1 by g. Hydraulic efficiency. Now we have to find out the efficiency. So efficiency means output upon input. Now here we have to find the hydraulic efficiency. So hydraulic efficiency means we have to find the efficiency that will be derived from the water power. Okay, so here we have the input, that is the water power, and output, that is the work done by the runner. Okay, so here the work done by the runner is rho q VW1 U1, and the relation of water power, that is rho q GH. So if you put here rho q GH, and here we have also rho q VW1 U1. So rho q, and here we have rho q. So rho q will get cancelled, and the remaining term will be VW1 U1 upon GH. So this relation is used for finding the hydraulic efficiency, that is VW1 U1 upon GH. Now we will see some working proportions for a Francis turbine. So first in that we have the flow ratio. Flow ratio, that is the ratio of the flow velocity to the theoretical velocity. So flow velocity, that is VF1, and theoretical velocity we have under root 2GH. Okay, so KF, that is the notation used for the flow ratio, that is equal to flow velocity upon the theoretical velocity, that is VF1 upon the under root 2GH. If you have to assume its value, then you can take its value in between 0.15 to 0.3, that is the value of the KF. Then second is the speed ratio. Speed ratio, that is again the tangential ratio of the tangential velocity to the theoretical velocity. So that is U1 upon under root 2GH. Okay, so that is its value is vary between 0.6 to 0.9. Then we have the ratio of width to the diameter. So the ratio of width to the diameter, that is denoted by N, and width, that is denoted by capital B, and diameter of the runner, that is denoted by the capital D. So width, ratio of width to the diameter, that is B1 by D1 and from 0.1 to 0.45. Okay, so the ratio of width to diameter, that is N1 is equal to V1 by D1, and its value varies from 0.1 to 0.45. Okay. In next part, I am going to explain you about the design procedure of the Francis turbine. Okay, so we'll see the next part in our next video.